So welcome to the class Computational Neuroscience, Neuronal Dynamics of Cognition. This week we will look at so-called continuum models. They are also called field models, and they can be used to describe cortical perception. Our brain consists of neurons, thousands of neurons, hundreds of thousands of neurons. These neurons are organized in populations, and these populations can do impressive things. You can do impressive things. Let me give you two examples. First, humans are pretty good at perception, at visual perception. For example, I can show you two gray rectangles and ask, do they have the same gray value? And if I shift them close to each other, it's pretty easy to see that one is a bit darker than the others. So what we exploit here are contrasts, and these are fairly weak contrasts, weak differences between the two rectangles. And we also exploit that the world is continuous. So this is our first example. Now let's look at a second example. The second example is our sense of direction. Look around your room. I suppose you sit in a room. And now close your eyes, really close your eyes, and turn your shoulders and point your nose to the door through which you entered. Now open your eyes, and you will see that you pretty much look at the door. This is an indication that you have a good internal compass. And this is the sense of direction, this internal compass, that we would like to explain with the field models, with the continuum models that I discuss this week. So, visual cortex consists of different neurons, different populations of neurons. They interact with each other. And if you want to understand this sense of direction, if you want to understand visual perception, it's good to have a nice model of these interacting populations. So far, we just looked at one single population, and we found that in this single population, if it's fully connected, then each neuron receives the same total input current. So each neuron sees the same mean driving field, and that's why it's called a mean field theory. And here's a summary slide of the argument. If you look at the input to neuron I, and if we say that each spike contributes some synaptic current, we sum up, and since the interactions are all identical, so each connection has the same weight, then this sum over all spikes, all neurons, just gives the population activity. If, moreover, we assume that this pulse here is an ultra-short current pulse, so formally with the Dirac delta function, we can just say it's q times the delta of s. Then you integrate this out, the integral disappears, and you see that the current is just the population activity, plus, of course, the external current. So each neuron is driven by the population activity. It's driven by the activity of all other neurons. And this is something we are going to exploit today. Now, these mean field arguments work not just for full connectivity, but also for random connectivity. There are two versions. You can keep the probability of a connection P fixed, like 15%, or you can say the number K of inputs per neuron is fixed, and this number stays the same if I increase the size of the network. In both cases, it's called random connectivity. Now, the argument so far did not make any assumption about the type of activity. But if we assume that we are in a stationary state means that the population activity is more or less constant as a function of time, then in this case, since all neurons are the same, the spatial average, which gives you the population activity, is the same as the temporal average, and that means that the population rate or the population activity is equal to the single neuron rate, but the single neuron rate can be calculated from the gain function, the frequency versus current curve of the neuron. And therefore, we can predict the population activity from single neuron properties. The mean firing rate, this frequency, can be defined as the inverse of the mean interspike interval. So what we have seen last week is that a single neuron embedded in a homogeneous population is driven by the population activity of all the other neurons in that population. Importantly, all neurons in a homogeneous population receive the same input, and these mean field arguments work for fully connected and randomly connected populations. Now, all of this works for time-dependent input, time-dependent activity. Now, if in addition we know that we are in a stationary state, then the single neuron firing rate is equal to the population activity, and in the stationary state, the population activity can be predicted by the single neuron gain function, also called the FI curve, the external input, and the intra-population coupling strength. Now, in the stationary state, the choice of neuron model is irrelevant. The only thing that counts is the gain function, also called FI curve. Now, this is not necessarily true outside the stationary state. So for this week, the mathematical aims are to go beyond stationary states. Now, how about transients? If I switch on a current, how does a population react? And I would like to have more than one population. I would like to have interacting populations. I would like to have many populations. And then the question is, can we write down a continuum of populations? These are the mathematical aims. Now, in terms of cognitive modeling, our aims are to describe a few effects of visual perception and the sense of direction that we had discussed before. We'll have to do quite a bit of math to arrive at the so-called field equations. These field equations are intrinsically continuous, and this continuity reflects the fact that the world outside is continuous. So we have to do a bit of work, but it's worth the effort, because in the end we will be able to apply our field models to our sense of directions, the internal compass, and to our sense of perception. So it's worth doing it. Stay tuned. We'll do a bit of work, but please stay on.